Part E. In this part, I will give you hints for our homework assignment number 1. Yeah. All right, the first part, E.1, part 1, 3 questions. Question number 2, 3, and 7. Yeah. Question number 2. Yeah. For this question, yeah, I give you 2 functions. Yeah. So these 2 functions very special. So you can see many zero, pretty big number. Another one, many digits after the decimal point, 1 point, that kind of thing. Very close to 1, but not equal to 1. Slightly different. Now, we want to compare these 2 functions. Which one is larger? Which one increases faster for the long run? Long run, okay? Yeah. Where n very, very large. Yeah. All right. So the question of this one, if you just answer it based on your intuition, it's very likely you will get the wrong answer based on your intuition. Yeah. Because your intuition is based on your experience. If you do not have a lot of experience, it is very likely your intuition is wrong. Okay. Yeah. Another thing for this kind of questions, you cannot do experiments. It is not realistic to do experiments. Think about you plug in number n to the 1 millionth power. How can you do the calculation? You cannot. Okay? Look at this. 1.00, although many zeros after the decimal point 1, but when n is large, for example, n equals 1 billion, can you do the calculation on that function? You cannot. Okay? Yeah. So that means doing experiments is not realistic. So you can only answer this question based on our mathematical theory. So I want to check your understanding on using our results. Some of the result in our notes. Okay? Yeah. Here, I like to use our comprehension question set 2, part B, question 2. We have a similar question. Yeah. In that one, we compare these 2 functions. Although, much smaller or much easier than our homework question. Yeah. But the theory background exactly the same. Yeah. In this one, the question is slightly different from our homework question. Which of following growth function corresponds to faster algorithm? Faster algorithm corresponds to the function that increases slower. If it increases very fast, then that means your algorithm is slower, right? Just the opposite. Yeah. So here the question's opposite. Okay. Yeah. So increases slower. Okay. Yeah. That means these 2 functions, we need to pick the smaller one. Okay. All right. So then, how do we compare these 2 functions? We need to use our theoretical result. Yeah. Okay. Yeah. In our theoretical result, this is an exponential function, a to the nth power with a greater than 1. It's an exponential function. Okay. The second one, it is a polynomial function, special polynomial function. here you can see basically we compare an exponential function and a polynomial function. Which one grows faster? Which one grows smaller? Right? Yeah. Here I want to recall one of our results. So we compare these two functions using limit. Okay. We take the limit when n goes to infinity. We use a polynomial function n to the dth power. So d just any constant exponent number, positive constant exponent number. Then a denominator exponential function, a to the nth, but base a greater than 1. That's important. Okay, not less than 1, greater than 1. Yeah. All right. And we use L'Hopital's rule to calculate this limit. So you can go back to find our notes, to find the computation part. Here, I do not want to repeat that computation part. Okay, we have it in our notes. Yeah, just find it. Here, I just give you the result. Result is 0. What's the meaning of 0 here? The 0 here means the exponential function dominates any polynomial function for the long run. Yeah, so the long run. Because go to infinity, so that corresponds to for the long run, right? Yeah. So here you can see this is the theoretical background for this question, this type of questions. Yeah. If you understand all these things, then you won't miss our homework question here. Yeah. But read the question carefully. Increases faster, algorithm faster, the meaning just the opposite, right? So these two meanings just the opposite each other. Yeah. So do not get confused. Yeah. All right, so that's the first question of this E.1. The second question, which of the following expression equals the seeding function of log base 2 of 2s minus 1? This question, I want to check your knowledge related to the seeding function, floor function of log base 2 function. Now, we have a formula. So there is an important formula I took from Appendix B in our textbook. Yeah. In my notes, I use that formula several times. So that is a very important formula for this class. Yeah. Here, I like to use another comprehension question, set 3, part B, question 12. Yeah. Similar, yeah. Here, ABC, yeah. And we use this formula. This is the formula I'm talking about. The key formula I'm talking about. Yeah. Use this formula. Yeah. How do you know B is correct? Okay. Here I do it for you. Because in the comprehension question, I only give you the answer. I didn't explain why this answer is correct. So now I do it here. Then, after you understand this example, you can use the similar way to solve our homework question. All right, so let me work on that. Okay. The parenthesis, the whole thing, we treat as that n variable. So one single variable. Yeah. Here, yeah, so let me apply this formula on this one. Okay. Yeah. Log base 2 parenthesis 2n plus 1, the whole thing. All right. One single number, yeah. And the right side, I use the formula, the ceiling function minus 1, right? Ceiling function log base 2, that 2m plus 1 plus 1. Yeah, because this m plus 1. So plus 1 minus 1. Because this plus 1, after I move to the left-hand side, I should minus that 1. Or we can treat as we subtract 1 both sides. Yeah, either way, we can get this right expression. All right, so this whole thing, 2 times m plus 1. Okay, yeah. Product of logarithm. Okay, so log a x times y, we use this property. Log base a of x plus log base a y. Okay, we use this property. Here we have log base 2 of 2. The first factor plus log base a of m plus 1 minus 1. Okay, yeah. Then log base 2 of 2, that's 1. 1 is an integer. Integer, we can pull it out of the ceiling function, right? Remember, we have a function, ceiling function of x plus m equals ceiling function x plus n. So we can take that integer n out of the ceiling function. Okay, so here we take this 1 out of the ceiling function. 1 and this minus 1 cancel out. So the answer is ceiling function of log base 2. Yeah, our 2 is, yeah, here, our a is 2. The current example. And m plus 1. So that is the B option. That is the B option. Okay. All right. I hope you understand all the detailed steps I used here. Then you can answer our homework question number 3. Yeah. All right. So that's the second question. The third one, number 7. Which of the following growth functions has the highest order of growth? Highest order of growth. You know the meaning of the growth function, highest order, right? Yeah. So here, let me just give you an example. Log n log n squared, okay? In order of growth, in increasing order. Yeah, if we compare these 4 functions, yeah, log of n, we know, much lower than n. Remember, we have this limit is log of n over n equals 0. We did that. L'Hopital's rule. Okay, L'Hopital's rule also. Yeah, so that means it has slower growth order of growth. Yeah. So then n slower growth order than n log n, then slower than n squared. Okay, yeah. So that's the basic meaning. Here we want to compare the growth order for these 4 functions. To compare that, I'd like to introduce a basic formula in logarithm. So that is a to the log base a of n equals n. So this formula is important. Okay? Yeah. With condition a positive and a not equal to 1. That's the condition. Otherwise, Otherwise, the log is not defined. Log base A of n is not defined. Okay? All right. Why is that? Here, let me show you why it is correct. Yeah, so because you may wonder, yeah, so why we can have this formula, right? Yeah. So let me quickly show you because it's pretty simple. Let x equals a to the log base a of n. So we assume x equals that expression. Now we take log base a both sides. Okay, log base a both sides. The left-hand side, log base a of x. Right-hand side, log base a of n times log base a of a. Log base a of a equals 1, right? So 1 times the first parenthesis, the same number, log base a of n. So you compare log base a of x equals log base a of n. That means x equals n, right? X equals n. So that is, we have this formula. Okay. All right. Then, why this formula is useful? Yes. So here we need this formula to help us simplify the 4 given functions. The first one, it's easy because we take a equals 2, right? So we apply our formula. This first function equals n. The last function, a equals root 2, right? So we apply that formula. This gives us n again. So you see, A option, D option, both n. Now the question, how about the D option? D option, it looks like we cannot apply the formula directly, right? Base 3 and the log base natural log E, they are different. How can we apply that formula? It's true, although we cannot apply that formula directly, but we can apply indirectly, right? After we do some transformation, then we can apply that formula. So let me show you how to do it. Okay. All right. So let me just work on B option. I leave E option to you. So you can use my way to get your result for B. For C. Yeah. All right, so now look at the B. Okay, B case. We have the function 3 to the natural log of n. Yeah. How do we simplify that form? Yeah. All right. Because base 3 is different from the log base E. But can we write 3 as as base E to some number? Can we do that? If we can, so we convert it to the same base. Okay, so the first thing is we want to write 3 as E to some number. Let me still write X. How about that? E to some special X equals 3. Is it possible? Yes, it's possible, right? Yeah. Because we just take a natural log both sides. Natural log of 3 equals what? Equals x, right? Equals x. The right-hand side, when we take log base E, we get x. Okay? So in this way, we have the expression for x. So then 3 equals E to the natural log of 3, right? Yeah. So you can see, so this formula, just another way we apply, the key formula for this question. That key formula, yeah, A equals E, right? So here we use A equals E, N equals 3. See, we apply that. So now we can write that 3 to the natural log to the n. This time we replace 3 by E to the natural log of 3, whole parenthesis to the natural log of n. How about that? A little more complicated, but we will quickly simplify it. Yeah. Then, exponent part based on the exponential function property, yeah, equals e to the product of those two numbers. Natural log of 3 times natural log of n equals that. Okay, all right. Then another time, natural log of 3 is a positive number, right? We use another logarithm property. This number, we can put it as at the exponent of that n. Okay, yeah. So we can put there. So then we write e to the natural log n to the natural log of 3. How about that? How about that? Okay, all right. So now e to the natural log something, is that this formula matching that formula? E equals a here. E equals a. So then this parenthesis corresponds to that n. Okay? Yeah, because that n not necessary integer. This for non-integer and also correct. Okay? Also correct. Yeah. All right. So we get the n to the natural log of 3. So that's the simplification of B option. B option, we can rewrite it as n to the natural log of 3. How about that? Okay, natural log of 3, you can find that value using some special calculator or some online computing tool. Okay, all right. Then option C, can you do the similar thing for this option C? Okay, n to something, n to some number. After that, because all 4 expressions using the same base n, their exponents are different. Okay, and we want to get the highest order. You want to take the largest exponent among 4 options. How about that? Okay, yeah. If you can get all these things, so you can see a lot of work you need to do. Yeah. But if you have pretty good math background, you can get it. Okay? Yeah, you can get it. Yeah. All right, so let me stop here and finish our part E.1.